Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by various people. We are now discussing the concepts of time varying fields. In the previous module, we have seen the Faraday's law, the Lenz's law, electric field due to the induced EMF, and the modified Maxwell's equation for electric fields. In the current module, we would discuss the validation of Ampere circuit law for time varying fields. That is, we will check whether the Ampere circuit law, as we know, is it valid even for the time varying fields or not. The modified Maxwell's equations for magnetic fields would also be given, and then we would try and get the updated Poisson's equation for magnetic and electric fields. For static fields, from Ampere circuit law, which says that the circulation of magnetic field intensity over any closed path is equal to the current enclosed by the path. So by applying Stokes' theorem to this, we have obtained del cross H bar to be equals to Z bar. Now, the principles of vector algebra say that the divergence of curl of any vector to be equals to 0. That is, if I take any vector v bar and if I calculate the curl of it, then it is a solenoid vector. In fact, we have discussed the same when we have discussed about the vector magnetic potential. That is why, because del dot b bar is equal to 0, b bar could be written as del cross a bar is vector magnetic potential, a bar. Right? So, if I follow the principle even to this equation, then I should get the divergence of curl of H bar to be equal to 0. Let us see if that is the case or not. If I apply the divergence operator on both the right hand side and the left hand side of the expression, I get that the divergence of curl of H bar to be equal to divergence of the current density. If you remember the continuity equation while discussing the electric field inside conductors, and in the video I have discussed the continuity equation from 3930 to 4130. So if you go and watch this again, you know that the continuity equation dictates that the divergence of current density to be equals to minus dou rho v by dou t, because the number of the total current flowing outward from any closed surface is equal to the number of charges which are leaving the closed surface. So divergence of Z bar to be equals to minus dou rho v by dou t. So in actuality, for this, because it is not equal to 0, for this to be equal to 0, the divergence of curl of H bar should not be equal to divergence of Z bar plus, it should be equal to divergence of Z bar plus dou rho v by dou t. Then the divergence would be equal to 0. This is what it should have been written as. But from Gauss divergence theorem, we know that rho v can always be written as the divergence of electric flux density. That is, rho v is equals to del dot b bar. So if I rearrange the term, I would rearrange the terms as, because the differentiation with respect to time and the divergence both are interchangeable, because both are linear operators, I can apply one after the other in any order and that will not change me the result. So I can rewrite this to be divergence of dou d bar by dou t. Because both are linear operator and the order change does not change the result. So if I combine these two, I can rewrite them to be divergence of z bar plus dou d bar by dou t. The divergence of curl of h bar is equal to divergence of z bar plus dou d bar by dou t, which implies that curl of magnetic field intensity is equal to z bar plus dou d bar by dou t. So this is the modified Maxwell's equation, or I can also say this is the modified Ampere's circuit law for time varying fields. One thing which I would like to know is if d bar is not time varying, if it is a static field, then dou d bar by dou t would be equal to 0 and del cross h bar is equal to z bar, and it is not violating the Ampere circuit law for static fields. But it is not applicable for time varying fields. For time varying fields, it is del cross h bar is equals to z bar plus dou d bar by dou t. This dou d bar by dou t is called as the displacement current density, because this is the current because of the change in electric flux density, that is displacement of charges. Hence it is called as the displacement current density, and it is generally represented as ZD bar. I would discuss what is the difference between conventional current and displacement current, such that it would be easy for you to identify when will there be displacement current and when will there be a conventional current. Let us consider a conductor of this shape. Then the current density Z bar is pointing outward. Now you know that for any area, the relationship between the current passing through the area and the surface current density is given as integral of Z bar dot ds bar. This is for any surface. If you consider a closed surface, then the current leaving any closed surface, the net current leaving any closed surface is equals to integral of closed surface integral of z bar dot ds bar. So in other words, I can write that closed surface integral of z bar dot ds bar to be equal to the current flowing outward minus the current coming inward. But what is current? Current is rate of engine charge. But what is current? Current is movement of charge. Therefore, I out can be written as charges leaving in a given time, and I in can be written as charges entering in a given time. Because the observation is made for the same time duration, I can rewrite this expression to be equal to charges leaving minus charges entering per given time. The charges leaving are represented as Q out and charges entering are represented as Q in. Now, if you have conventional current, You pretty well know that conventional current is because of change in potential difference, and the conventional current flows only if there is an applied external electric potential, and it should form a closed path with this conductor, right? Now, what happens in this conventional current is all the charges, all the positive charges are collected by this negative terminal, and these collected charges are ejected by this positive terminal, and they keep moving. As many number of charges which are collected here will be ejected by the positive terminal. Therefore, the number of charges which are entering this conductor will always be equal to the number of charges which are leaving the conductor. That is, no charges are being lost or no charges are being gained. That means there is no change in charge concentration. Q in is equals to Q out. Therefore, there is no change in charge concentration. The meaning of no change in charge concentration written in mathematical form is dou rho v by dou t is equal to 0. Because rho v is the charge concentration, dou rho v by dou t is equal to 0. Now, if we are discussing the displacement current, from the name itself, there are two terms, displacement and current. The word current refers to movement of charge carriers. So, if there are charge carriers which are moving, they produce current. This is something which we know already. But what is displacement current? You consider a body, and initially there are 5 charges, 5 coulombs of charge inside. Now, for some reason, these charges have gone down and they have come to only 3 coulombs of charge. Let me say, maybe because of electron hole recombination or whatever might be the reason. We are not bothered about the reason, but we just know that earlier there were 5 coulombs of charge, but right now there are only 3 coulombs of charge. So that means I can put in one way that charges have left the surface. How much change has occurred? How much charges have left? 2 coulombs of charges have left the surface. Now, 2 coulombs of charges have left the surface. That means the charges left is 2 and charges entering is equal to 0 by time t. This is, for example, if the time is 1 second, if the time of observation is 1 second, then 2 amperes of current has been observed. And this current is called as displacement current. Let us consider one more scenario. I have 5 coulombs of charge earlier, but for some reason this body has gained the charge. And how much it gained? It became 10 coulombs within 2 seconds. That means this body has received 5 more charges. So what is the current leaving this body? The current leaving this body is 0 because there have no charges left, but 5 charges have come in within 2 seconds of time. That means the current leaving this body is minus 2.5 amperes. These currents which we are talking, They are not because of some electromotive force. They are not because of some potential difference. These are not conventional currents. These are currents because of there is change in the charge concentration. Displacement current is due to the change in charge concentration. Therefore, in this, the charges entering would not be same as charges leaving. That is, dou rho v by dou t is not equals to 0. Because what is Q? Q is nothing but volume integral of rho v. So if I rechange this expression, I can write that the closed surface integral of Jd bar ds bar to be equals to volume integral of dou by dou t of rho v dv. If I rechange this expression using divergence theorem, what does divergence theorem say? Divergence theorem say that any closed surface integral can be rewritten as the volume integral with respect to its divergence. So the volume integral of divergence of z bar dv is equal to, as you know, this rho v can be written as the divergence of d bar. Again, if I rechange this order of differentiation, I can get this to be divergence of dou d bar by dou t dv. And if these two integrations are to be equal, the integrands must be equal. That means del dot j bar to be equals to del dot dou d bar by dou t. That means jd bar should be equals to dou d bar by dou t. That dou jd bar is called as displacement current density. The source of displacement current is time varying electric flux density. Now, if there is no time varying electric flux density, then there is no displacement current density, then del cross h bar can be just z bar. But if there is a time varying electric flux density, then del cross h bar is to be equals to z bar plus jd bar, that is dou d bar by dou t. So the updated Maxwell's equations for magnetic fields are divergence of V bar is equal to 0. There is no change in this. This is kept same. But the change is in the curl of magnetic field intensity is no longer Z bar. It is equals to Z bar plus dou D bar by dou T. These are the updated Maxwell's equations in the case of magnetic fields. As we have seen in the contents, the next concept we will be discussing is how to get the Poisson's equations. The Poisson's equations are defined for potentials. So let me discuss what is the effect of this time varying nature on these potentials. You may remember that the magnetic potential is defined on magnetic flux density. From the equation del bar dot V bar is equals to 0, we have said that because this is a solenoidal vector, this B bar can be written as some curl of A bar, a vector magnetic potential. Now, because this equation has no change, there is no change in the vector magnetic potential. But the scalar electric potential is defined from the fact that del cross E bar is equals to 0. And we know that gradient of any scalar field is an irrotational vector. Because gradient of any scalar field is an irrotational vector, del cross E bar is equals to 0 where E bar is an irrotational vector. Therefore, E bar was equal to minus del V. So that is how we got electric potential, scalar electric potential, and negative sign to indicate that work done in moving a body from point A to B is in the direction which is opposing the direction of electric field intensity. So having said that, we have already seen that for time varying fields, del cross A bar, E bar is not equals to 0. Instead, del cross E bar is equal to minus dou V bar by dou T. Therefore, this electric field is no longer irrotational. So what is the relationship between the electric potential and the electric field in presence of time varying fields is what we would discuss, and that is what we title the discussion called as time varying electric potential. We have already seen that the curl of E bar is equals to minus dou V bar by dou T, but you may remember that the B bar itself is curl of A bar, a vector magnetic potential. Therefore, I can rewrite this del of E bar to be equals to minus dou bar dou by dou T of del cross A bar. So I can rewrite this expression to be del cross E bar is equals to minus del cross dou A bar by dou T. If I take it to my right hand side, so left hand side, I can get that curl of E bar plus dou A bar by dou T is equal to 0. Now this is an irrotational vector. Because this is an irrotational vector, I can express this to be equal to gradient of a scalar field minus del V. So my electric field E bar is equals to minus del V minus dou A bar by dou T. Again, remember that if there is no change in magnetic field, then there would be no change in the magnetic potential. If there is no change with respect to time in magnetic field, then there would be no change with respect to time in vector magnetic potential. Then this equation would still be equals to E bar equals to minus del V. But in the presence of time varying fields, E bar is equal to minus del V minus dou A bar by dou T. This is called as the electric field in terms of the electric potential and the vector magnetic potential. Now that we have obtained the expression of electric field intensity in terms of the scalar electric potential in the vector magnetic potential, let us try to determine the updated Poisson's equations for magnetic field. So if we calculate the curl of a magnetic flux density, then del cross B bar is equals to mu times del cross H bar, because B bar is equals to mu times H bar. So if I calculate the curl of B bar, it is mu times del cross H bar, from Maxwell's equation, we know that del cross H bar to be equals to J bar plus dou D bar by dou T. And we also know that D bar can be expressed as epsilon times E bar. Therefore, del cross B bar is equals to mu times J bar plus epsilon times dou by dou T of E bar. But we have obtained the expression of electric field intensity to be equals to minus del V minus dou A bar by dou T. If I substitute these in the above expression, I would get del cross B bar to be equals to mu times J bar plus epsilon times dou by dou T of minus del V minus dou A bar by dou T. But we know that B bar is equals to the curl of vector magnetic potential del cross A bar. So del cross A bar is equal to, by taking mu inside, mu J bar, and it is minus here, so minus is brought here, minus mu epsilon dou by dou T of del V minus mu epsilon dou by dou T of dou A bar by dou T, that is double differentiation with respect to time, dou square A by dou T square. And I can remodify this expression that by changing the order of differentiation, I can rewrite this to be mu J bar minus mu epsilon times the gradient of dou V by dou T minus mu epsilon times the double differentiation of A bar with respect to. From the vector identity, I know that the Laplacian of any vector field is equal to the gradient of divergence minus curl of curl. So curl of any vector field can be written as the gradient of the divergence minus the Laplacian of the vector. So from this, I can write that the gradient of divergence of A bar minus Laplacian of A bar is equals to mu J bar minus mu epsilon times gradient of dou V by dou T minus mu epsilon times dou square A by dou T square. This is the result which we got earlier. Now, coming to A bar, we know that A bar is not unique and divergence of A bar can be set to any wish of our liking, but it still won't affect any other quantity because A bar is not unique. So if we set the divergence of A bar to be mu epsilon times dou V by dou T minus mu epsilon times dou V by dou T, then this value and this value both cancel out. And what I would be getting is dou square A minus, if I bring it outside, minus mu epsilon times dou square A by dou T square is equals to minus mu J bar. This is the Poisson's equation for time varying fields. Poisson's equation for vector magnetic potential. You may remember that the Poisson's equation and Maxwell's equation differ in one basic entity, that Maxwell's equations are defined for magnetic flux densities and magnetic field intensities, whereas the Poisson's equations are defined for the potentials. They are either defined for the vector magnetic potential or scalar electric potential. So Poisson's equation for vector magnetic potential is that the Laplacian of A bar minus mu epsilon times dou square A by dou T square is equals to minus mu J bar. If we try to obtain the updated Poisson's equation for electric field, I would start with the divergence of B bar, that is the divergence of electric flux density, to be the charge concentration rho V, and using the expression D bar is equals to epsilon times E bar, I can say that the divergence of electric field intensity to be equals to rho V by epsilon. But we have already established that E bar, the electric field intensity, can be written as the gradient of the vector potential minus V and the time variance of A bar minus dou A bar by dou T. Apply the divergence operator to this expression, I get that the divergence of del V plus dou A bar by dou T is equals to minus rho Y by epsilon this minus sign is obtained from the other side. Difference of gradient of V plus time variation of divergence of A bar is equals to minus rho V by epsilon. We have already set the divergence of A bar to be minus mu epsilon times dou V by dou T. Therefore, I can write that the Laplacian of V plus dou by dou T of minus mu epsilon dou V by dou T is equals to minus rho V by epsilon. Now, this is nothing but the double differentiation of the potential. So, this equation reduces to the Laplacian of V minus mu epsilon times dou square V by dou T square is equals to minus rho V by epsilon, and this is the updated Poisson's equation for scalar electric potential. Thank you for your attention. For any queries, please ask in the comment section.